You want to hold this while you...
Sure.
Yeah. It's warmer in here than the other beginning.
You will be automatically recorded.
Okay.
If you don't wish it to be published, we won't post it.
Okay. I'm sure it's fine.
Is it okay?
Okay, hi everybody. Welcome to the first colloquium of the fall semester. I am absolutely delighted to have Freeke here. So Dr. Freeke van der Voort is a world expert on galaxy formation and evolution, and also a longtime friend. Freeke got her PhD from Leiden University in the Netherlands, working with Joop Shea. And she then moved to Berkeley because I was there and just wanted to hang out together. But we did actually change the postdoc, I was looking this up, postdoc whiskey hour. We expanded it to include wine. I don't know if you remember those days. They were good days. She was also a postdoc in Taiwan, Yale, and Germany, just different positions, sometimes jointly. She is now a senior lecturer at Cardiff University in Wales, where she is continuing to expand the boundaries with cosmological simulations, and today talking about chemical enrichment of galaxies. Thank you so much for being here.
Thank you. Thanks for having me. It's great to be here and to reunite with some people I hadn't seen for 8 years. Is that an okay volume? I don't want it to be too close. Or again? Yeah? Okay. So yes, this is very high and big. So I will talk about like basically the gas that lives around galaxies, and then how it's affects the galaxies inside, and also how the galaxies change their environment. But I wanted to first just give you a broad overview of why, even if you don't care about the very specific details of what I'm telling you about, I still think that it's really, this field is very much embedded in like different aspects of astrophysics, because galaxies connect to a variety of other subfields in astronomy. So they serve as beacons of light, which you can observe and then use as a tracer of the large-scale structure of the universe, and thus they connect to cosmology. But they are also the hosts of like a variety of other cool phenomena, like star formation, supermassive black holes, and all of the feedback, the outflows that they drive. So it's really connected to maybe everything except planet formation directly. Although, you know, we do. So I hope I'll have time to also talk about chemical enrichment, which of course is done by stars. But then it's still the large-scale gas flows that distribute these elements throughout the cosmos, which then reaccrete onto galaxies and then set the future metallicity of your next generations of stars, which then also affects planet formation. So there we are. Ta-da! So how I do this is by using cosmological simulations, and there are benefits and downsides to any method that you use in astronomy. One of the very powerful things in cosmological simulations is that we have exceptionally well-defined initial conditions, because we get them directly from the cosmic microwave background. So from observations, this is the photons that currently have a temperature of about 2.7 Kelvin. The tiniest fluctuations that are measured of order 10 to the minus 4 grow out into the structure that we see today in the universe. And I have a movie that shows you in just a moment. So this means that we have, in a way, no actual control over exactly how structure forms, because this is all set by the initial conditions that we know from the CMB and by the laws of physics, such like primarily gravity for large scale things. So here I think is the movie. So in the beginning of the universe was very homogeneous. This is the gas density that you're watching. So any of these tiny fluctuations are growing into bigger structures. Then they, they will eventually form this more familiar structure of the large-scale cosmic web. So you have sort of the one-dimensional sheets, two-dimensional filaments, and then in the centers of these filaments and also embedded within are like three-dimensionally collapsed structures. All of this, so I told you this is the gas you're watching. You're watching like a cluster form here in bright red and orange, cluster of galaxies in bright blue. That's the voids where like there's sort of less excitement going on when you think about galaxies. The galaxies themselves you can't actually see. They would be like 1 pixel each in this image. This is just giving you a 100 megaparsec view of the structure of the universe. The universe, of course, is bigger than 100 megaparsec, but it's a balance you have to strike between what kind of statistics do I want for my study of galaxy formation, and the bigger you make it, though, the less resolution you have inside the collapsed structures that you're wanting to study. So 100 megaparsec is kind of, it'll give you some large structures and still enough resolution to sort of study the Milky Way mass scale. But if you want to go really into more detail, you can do something else that I'll talk about in a moment. So this is an artist impression from a review that Rob Crane and I wrote like 2 years ago, I guess, just to illustrate what kind of things that we think about when we simulate these large-scale cosmological simulations. So we have to think about, of course, the actually largest scales of the universe, which you can see over there. So we've decided to put this in centimeters. So that's 10 to the 28 centimeters. We don't get that far. That would just like really reduce our galaxies to like a single resolution element, which is not what we want. So then you go, galaxy clusters are still quite hard. Then we have the gas around galaxies, or the circumgalactic medium, or I'll also call it the CGM, which we do much better at. Galaxies themselves, the structure of the interstellar medium starts becoming really difficult. Then, of course, galaxies are affected by the stars that form. If they're grouped, the supernova that will go off are then also clustered, and this will drive large-scale outflows rather than just a local supernova remnant. Then you have the separation between stars, the separation in between binaries, supermassive black hole accretion disks, which also in some complicated way that nobody fully understands, like drive outflows. The stars themselves, they evolve and they blow, they release material, they make more heavier elements, and then cooling. So gas cools primarily by particles interacting with each other. So it's also in a way the spacing between individual atoms that also comes into play. So all of this we cannot resolve, of course. We don't do individual atoms and ions and electrons, but we do put this in an approximate way using tables, using cooling tables, using yield tables for stellar evolution, and using models that we're hoping that create the large-scale effects that we think are important for galaxies without resolving the small-scale scales. So small-scale scales that where they actually. Yeah, I guess so. Where they actually occur. Well, we don't do individual supernovae, but we put in a very basic model that then is based on how much energy is released in total and drive these large-scale winds. So we have to do this because galaxy formation turns out to be very inefficient. So if we didn't have any observations, we would just be done. We would be like, well, gravity, everything collapses. There's some like rate of how fast stars form, and then that's it. But here's just a simulation showing you that if you had a cosmological simulation without any outflows, either driven by supernovae or by supermassive black holes, we would end up with 10 times as many stars. We would have more galaxies, they would be more awesome, they would be more massive, and it's not what the real universe is doing. So like observations have told us that that is not how it works. So now we have spent a long time putting in these large-scale outflows and trying to make more realistic galaxies that we didn't get like 15 years ago, our galaxies didn't look at all like the ones in the real universe, and now they do. Well, but why am I still talking to you then? Well, so these cosmological simulations are useful because they can help you sort of connect different redshifts. They can help you study how the galaxies, came to evolve, why they have this structure. You can study the stuff around the galaxies, which is much harder to detect in observations. But now we have multiple different suites of simulations that claim that they make perfectly realistic galaxies that are fine for these purposes, but they do this in very different ways. So here's an example from illustrious TNG up on top. So they make disk galaxies and or blue galaxies and red galaxies, and then there's the Hubble tuning fork with early type or red galaxies, and then also disk galaxies. So they make all these different types of galaxies, but how do you tell which one is then the more true representation of the universe? Both of them will have issues, of course. So one thing where I wanted to show you, I could show you many different things, but this is a talk focused on the gas around galaxies. So I'm showing you the gas inflow rates and the gas outflow rates for these two simulations, Eagle and illustrious TNG, for 3 different masses. This is in halo mass, so it goes, the blue ones is sort of Milky Way mass, 10 to the 12 solar masses. So solid is Eagle, and the dashed is illustrious TNG. And if you look at very large distances from the galaxies, they're pretty similar. That's because on these scales, it's mostly set by gravity, and all these processes that are specific to the gas and specific to galaxies are not yet that important. But in the center, they can be an order of magnitude different. So one simulation has much higher inflow rates and therefore needs much higher outflow rates in order to make a realistic galaxy so that they don't grow far too massive. The other one really suppresses the inflow rates. Like the gas just never makes it into the center, so they also don't need which of course takes a lot of effort to do this, probably at high redshift. And then it doesn't have to push quite as much at low redshift. This is a redshift 0 plot. So just showing you that there are these very different pathways to making a sample that is from just the stellar properties and the morphology of the galaxy is not really distinguishable. So now the hope is that the CGM, the gas around galaxies, which must be different, right? Because now we have one simulation has loads of gas around and it keeps pushing it, and the other one that really sort of pushed a lot of the gas away out of the halo, and it's just not there anymore. So the hope is that this CGM can help determine which kind of picture is more realistic. So what we now think, we used to think about the CGM as just like some hot gas sitting around a galaxy. And this is like an artist impression from another review by Fauché, Giguère, and also last year. And this is how we currently think of it. It's a very messy structure. It's not actually just a hot ball of gas. It actually has multiphase structure. There's gas accreting, gas flowing out, gas just sort of sitting there in quasi-hydrostatic equilibrium, and all of this has structure. This is a sort of a low redshift focused talk, by the way, just so you know, it's a very redshift 0 focused for this talk. So, and then all of these outflows, they can cool, and they can create this cool clouds embedded in the hot wind. Then in the top left, you see an individual cool cloud, which has its own structure. And then in the top right, you can see the interface between the cool gas and the hot gas, which has this complicated interface. And it's all of these things that we think about, but of course cannot capture in a single simulation. I wanted to, so all of this structure depends, so both the physical structure that I just talked about, but also what it then looks like in observations when you go out and try and determine what the real universe is doing depends on a variety of physical processes from the galaxy itself, because it drives these massive outflows, but also in situ physics that determines what the CGM properties are. So one problem that we have is that our simulations aren't necessarily maybe including the right physics, and that's something you need to worry about. Maybe there's something else that we haven't included that is also vital. But not only do we have that problem, we also have the problem that maybe we don't get this same answer when we go to a higher resolution simulation, because it's not converged. And here is just an illustration that is not something that only cosmological simulations worry about, but is also true for idealized simulations. So this is just a cool cloud, that I like my cartoon here. It's like a hot wind in red and a cool cloud sitting there nicely spherical, and then it's being the hot wind is streaming, but in reality, of course, it would be the cool cloud falling through the hot gas in the halo. So what then these people did on very fancy, very high resolution subparsec simulations is try to see what happens then. So I did the same simulation setup and then did it at 3 different resolutions. So my simulations have like 100 parsec at best, kiloparsec, 5 kiloparsec is more like what I normally think about. These are sub-parsec simulations, and they're still not converged. So as you go to higher resolution, which is down to lower panels, the cloud gets accelerated less by the hot wind, and it breaks up in more, like a larger number of cold clumps. So there's no hope. If we can't do this in these kinds of simulations, there's no hope we can do this in cosmological simulations. Nevertheless, we are still going to try and see what happens when we add a lot more resolution to our simulation. So in order to do this, I don't want to simulate a large chunk of the universe. I want to focus on a particular object that I think is exceptionally fascinating. And for me, this is just a random halo that is somewhat like the Milky Way and isn't too close to other structures, because that makes it more complicated and more expensive to run. And then you can run zoom-in simulations. So you reduce the resolution in the rest of the universe, and you put all of the extra effort into getting one galaxy and its near, out to about 5 halo virial radii. Get that in extreme detail. So here you can see that this is now the starlight that you see. This is redshift 1.4. This galaxy is merging because everything is still forming hierarchically. And it's these types of simulations that I am using. But normally, what happens is that we keep. So this is run with a moving mesh code called a repo. The advantage is that, so you saw those voids, nothing happens there, so you don't really need crazy resolution there. And in the galaxies, like, there's lots of activity, star formation, etc. So we want lots of resolution there. The problem is, if you're like me and you want to sort of study something in between the circumgalactic medium, you're sort of spending all of your computational time on getting the galaxies right, because these are simulations that where the resolution, the spatial resolution increases as you go to higher density, because the resolution, like the mass resolution of each computational cell stays the same. So you can see that here. This is a density slice through one of those standard simulations that look really beautiful when you project them, because then you're adding like 200 kiloparsec worth of resolution elements. But this is a slice through these simulations. So inside the galaxy, we have 100 parsec resolution or so, and then out in the CGM, the density is very low, and these cells now are 5 kiloparsec in size or something. And so if you want to study the CGM, what the simulation is actually doing is spending all of its time thinking about the interstellar medium and star formation and all of the gas flows there, whereas I want to study the gas flows in the CGM. So what you can do is just say, OK, keep the ISM as you want, keep the stuff outside the halo as before, but give me an extra 2 orders of magnitude more resolution in the CGM. And this is actually very computationally efficient, because if you don't do this, then because these are distributed simulations, and a lot of them then just end up waiting for the galaxy to finally finish its thing, because the gas is on much smaller time steps because the density is so much higher. So these two simulations vary in resolution by a factor of 100, which sadly, because the universe is 3D, is only a cube root of 100 in spatial resolution, but let's not focus too much on that. And this took 5 times longer to run. So it's really efficient, because normally a factor of 100 would be like at least a factor of 200, if not more expensive to run. So what then happened? So there's good news and there's bad news. I'll start with the good news. So the galaxies actually don't supermind which is also maybe a little surprising, because you could imagine that if you get all of this additional structure, you see there's much stronger underdensities, many more of the cool clouds. They're very small, so they might be hard to see, but you get a lot more sort of like shocks and just a much better resolved gas around these galaxies. But the galaxies themselves don't care very much. They are the same mass. They are the same sort of shape. This galaxy is a little bit more blue, the one at the highest resolution. And I think that's maybe because at 500 parsec, we're really changing what happens very near the galaxy, but not really far out into the CGM. So what happens to the CGM itself, though, depends on what you care about. If you care about global properties, then nothing changes. So the top panel just shows you a projection of the density, and all of this is very similar. But if you were to go out and observe the CGM, for example, by looking at neutral hydrogen, which you can do either by 21 centimeter emission or in absorption around, like in background objects. I'll come back to how this works in just a sec. Then you can see that there's a lot more structure, a lot finer scale structure, and just a lot more neutral hydrogen. So because we're forming so much more cool gas, so 10 to the 4 Kelvin is cool for if you're thinking about halos around galaxies, and that's where the neutral hydrogen lives. So we get a lot more of this stuff. So if you wanted to compare to observations and you wanted to specifically know what happens to this part of the halo, you would have to be very careful modeling it correctly. And as I said, it's not converged. So here are this is an example of how you would then see it. You use a background light source like a quasar, has a very boring spectrum. So any features you see in it is gas that it has traversed through on the way to our telescopes, and then these absorption lines will tell you how much stuff there is. So here on the right is from cos halos, neutral hydrogen as a function of radius away from the galaxy. I must warn you that these are 40 very different galaxies that span at least 2 orders of magnitude in stellar mass and aren't, all the same thing. So, and I'm going to go ahead and compare that to one simulated galaxy. So it's completely not fair, but let's do it anyway. So here we then have the results. So if you count the number or the covering fraction of these absorption systems as a function of their strength, so how much neutral hydrogen there is, then you see that the original simulations, which are in blue, are massively underproducing the amount of neutral hydrogen. And people had claimed, like, oh, we don't understand anything about galaxy formation because there's not enough cool gas in our halos, and therefore our understanding is wrong and our simulations are wrong. So I fixed it by adding this extra 2 orders of magnitude of resolution, and then I broke it again by adding another order of magnitude of resolution. So it's still not converged. We still don't know what's going on. If we keep doing this, we will have all of the halo being cold gas, which definitely doesn't happen. So it's not necessarily a problem for everything we study, but you have to be super careful if you want to look at this very specific outliers basically in the distribution. And definitely I wouldn't claim anything is necessarily wrong with our fundamental understanding of the universe just because we are looking at something that isn't necessarily perfectly modeled. So I want you to so there's good things also, because a lot of the stuff that the halo is doing is perfectly modeled accurately. Just these very specific, unfortunately, most observable things are really difficult to do. So then I want to make this more complicated by talking about the in situ physics in the CGM, so the magnetic fields. So we start our simulations with a very small seed field at the beginning, so when we start running them at redshift 127, and then all of this seed field gets wiped out because structure formation will, the turbulence that happens will wind up the field lines, amplify them to much like orders of magnitude higher values, and it will therefore not have a signature of what we put in initially. This happens most, any turbulent eddy will be the fastest on small scale, so it'll happen first on the smallest scales, not the largest scales. So they amplify to like, to like 10% of the kinetic energy or so in the galaxy very efficiently, and maybe a little bit more once the large scale rotation of the galaxy also starts helping. And then it's brought out into the halo, into the CGM through outflows. And you can see that there's correlation. So these are two edge-on galaxies. On the left is where the magnetic field strength is high in sort of yellow-orangey, and then on the right is where the metallicity is high, and metals are also created inside the galaxy and then taken out by these large-scale outflows. So does this actually matter? So we have, so on the top right, you can see what the magnetic field strengths are. So they are in most, so this is a slice through the simulation, but the simulation is 3D. Most of the volume, the magnetic field strength is actually below 0.1 microgauss. If you convert this to pressure, which is done in the bottom panel, and compare it to the thermal pressure, you can see that in this bright red is where thermal pressure dominates by 2 orders of magnitude over the magnetic pressure. But locally in the outflow directions where the magnetic field is high and providing pressure support and therefore allowing some of the gas to exist in the cooler phase, it can actually be locally dominant. But globally, it's definitely the thermal pressure that dominates. So is this then important? Globally, it's clearly they're not relevant. So we end up with galaxies that have similar properties, but not quite the same. So any of our simulations that have no magnetic field. So the only difference, so we're still actually running the same simulation, the same MHD equations. We're just not putting in a seed field because 1,000,000 times 0 is still 0. So it's actually not like in this case, it's not like a numerical implementation problem. It's really just a matter of you either have no seed field or you put a seed field in. So the galaxies end up a little bit smaller, and I think this is to do with how the outflows are launched from these galaxies. Let's skip whether or not they match observations and just go and show you. You want to see that? Nah. There's not enough to really, in the galaxies they have reasonable field strength. In the CGM there aren't very many constraints, so it's not very telling yet. But invite me back in like 2-3 years, and then we'll have a lot more observational probes, so it'll tell us more about whether or not we're anywhere near sort of realistic magnetic field strengths in the CGM. So the effect then is, so here I'm showing you the metallicity, which is a combination of like how many metals are formed in the galaxy, how are they pushed out into the CGM by these giant outflows driven by primarily star formation, and then how do they mix in situ in the CGM. And on the left you see the one without magnetic fields, on the right it's with magnetic fields, and I think we can all agree that there are some striking differences. So in the case where we have magnetic fields, which I think should be our default given the fact that the universe also has magnetic fields, the outflows are much more collimated, and it mixes much less with the circumgalactic medium. So you have much more low metallicity inflows into the galaxy. The other thing that happens, which might be a little bit hard to see from here, is that you end up with magnetic pressure dominated thick, cool disk around the galaxy. So not the galaxy itself, but some sort of extended H1 disk. which helps, I think, to collimate the outflow so that there are some differences that happen inside the CGM because the velocity dispersion is smaller with magnetic fields, and therefore it mixes less in situ, but also the outflows that are driven actually have different properties because as they're trying to push out, they have a harder time moving all this additional dense neutral gas, or dense for the CGM, neutral gas around it, and therefore it primarily works in the center of the galaxy where the outflow strengths are high, and this then also takes the low angular momentum gas away, which then can pick up angular momentum out in the halo and reaccrete and make a bigger disk. I think that's so, but all of these things probably happening all at once. I here have some proof. This is the easiest one. Proof that the velocity dispersion is lower with magnetic fields. So I just put some dashed so you can see what it's like at 100 kiloparsec. So it's not quite a factor of 2, but the velocities of the gas in general are lower because it's now having to push through the magnetic field if it wants to not. Well, it has a happy time following magnetic field lines, but if it wants to push through any magnetic field lines, it has to do this extra work. So I'm still working on whether or not there's an additional component to the mixing, and I can't tell you that today. This always been very Milky Way mass focused. I just wanted to show you some work. So I had to flip like 90-degree rotate. So now the galaxy is like edge on still, but it's like vertical instead of horizontal, because otherwise it would be hard to show. But this is as a function of mass. So the halo mass increases by 0.5 dex for every step. So you go from dwarf galaxies, where you can see that the difference between the top and the bottom panel, which is with and without magnetic fields, is the bottom is with magnetic fields, is very small. At high masses, the difference is also very small, and it's really sort of this intermediate mass regime, 10 to the 11, 10 to the 12 in halo mass, so like 2 to 3 orders of magnitude lower in stellar mass, where it makes the biggest impact. This is that quantified. The top is the temperature, and the bottom is the metallicity. So especially if you focus on this. The metallicity panel, the bottom panel here in the middle, that's a halo that's just a factor of 3 smaller than the Milky Way. You can see the metallicity is really low in the outer CGM because the outflows are not managing to get the material out there. So that then, of course, also affects what they look like. So here we're back to a Milky Way mass galaxy. The top panel is the neutral hydrogen that you've already seen. You can look at other ions. So it's carbon-4, probes about 10 to the 5 Kelvin gas. Oxygen-6 about 10 to the 5.5. It's not quite the hot halo, but it's like getting there. So you're really sort of probing the different phases of the CGM, and you can see that between the left and the right one, we get very different behavior. So on the left, the outflows are managing to go in much wider directions than on the right, where it's really collimated and staying. The metals and the hot gas, the hotter gas, are staying really close to this polar direction. So I wanted to mention. So this is not one of my students' plots. This is what I did very quickly and then cut it out, and that's why it looks so ugly. But I want to focus on the 10 to the 13 solar mass halo, which is a small galaxy group, and there are basically no real differences between the two simulations with and without magnetic fields. So overall, they don't have a global impact, but if you look at specific galaxies themselves that are orbiting in this group, then you can still see that they're wildly different. So we have, I think, Thomas, this is my student Thomas, he has the other way around. So there's no magnetic fields now on the right, and with magnetic fields on the left. And this is quite a massive, like 10 to the, it's a little bit less massive than the Milky Way, but not by much, maybe 10 to the 10 in stars or something. And it's moving at about a distance of 100 kiloparsec from the center of this galaxy group. And you can see, I hope, visually, so we're talking about the big blob above the edge-on galaxy there, that the tail of material that's being stripped has very different properties and also probably a very different amount. And I show you the actual numbers here. So as this galaxy moves through the halo over about 1.5 gigayears, it loses twice as much of its total halo mass. This is not ISM mass, but total halo mass compared to a galaxy with magnetic fields. And this is likely because as it goes through the halo, if there are magnetic fields, then it gets sort of like protected by the galaxy moving through these magnetic field lines, and then you get the nice draping that protects them from being disrupted. That also means that if you then look at the tail, that you get a very different, so the tail, you can quantify how much material was previously in this satellite galaxy system versus what it looks like it is now. And this tail continues to mix. That's why it's such a large tail. It's not just the material that came from the satellite, but it seeds instabilities and matter condenses onto the tail. And you end up with a much larger amount of mixed gas when you don't have magnetic fields than when you do, just because mixing is enhanced. I want to make it even more complicated now by talking about cosmic ray feedback. Let me first mention that I think we disagree strongly about all of this with other simulation groups. So I told you that we have magnetic field strengths of about 0.1 microgauss in the halo. So not too many people have started worrying about magnetic fields, but FIRE has, the FIRE simulations, and they have about an order of magnitude lower magnetic field strengths, so they don't quite reach as high values as us, which means that that the effects that they see are much smaller. Just because if our sort of thermal pressure dominates by a factor of 10, so it goes as the square of the magnetic pressure goes as the square of the magnetic field. So if you then theirs is like an extra factor of, I don't know, not quite 100 than us, but close to that. So that also affects what you then do with anything that follows magnetic field lines, such as relativistic charged particles called cosmic rays. So we are not only disagreeing about the magnetic. So yeah, don't take what I tell you today as like the definite truth, but it is what we're getting, and there are we think that they are a reasonable possibility, but there are other possibilities. So, and this is what FIRE gets for a simulation where they just have magnetic fields, which are lower strength than ours, and then a simulation where they include cosmic ray feedback. So cosmic rays, if they are dominant, if their pressure dominates the halo, they can set up a strong pressure gradient, which can move gas out from the inner, from the center out into the halo. And this happens very efficiently in this case, where now the gas is just completely cosmic ray pressure supported and therefore no longer hot, and it's living at temperatures of 10 to the 5 Kelvin or so, rather than the virial temperature of, well, you can see it right here where you don't have cosmic ray feedback, of closer to 10 to the 6 Kelvin. Of course, this will then also have implication for what they look like in observations. So we have some model that has differences, but many more differences. So it may not be the way we model cosmic rays, which sets these differences. But let me just talk about what we do. So we have So when you model cosmic rays, you cannot do it properly because firstly, it would be too expensive, and secondly, we don't fully understand cosmic ray physics, so it would be hard to implement something that you don't understand. So there's a model where the cosmic rays move with the flow, where they diffuse compared to the flow, and where they lose energy because they interact with the magnetic field. This is called alphane cooling. And fire does this in a different way. They have different values, but they also have all of these aspects as well. So what we end up with is more compact galaxies. So this is the bottom panel compared to the top panel. This is a function of mass. So we end up with more compact galaxies when we have this feedback. And let's skip this for now and just say that, so here it is as a function of halo mass, how much mass gets moved, well, the mass outflow rate and the velocity of these outflows. And if you see that the cosmic rays are the downward pointing triangles, they basically overlap with the no cosmic ray simulations at high mass, and then for dwarf galaxies, there's a big difference. They can have outflows that are an order of magnitude stronger. This, of course, is more complicated in reality. Maybe this parameter that we use for diffusion actually depends on the density of the gas. So you can vary it to see what kind of difference this makes. So now we're zooming back out to the CGM picture, and here is a bunch of different properties: density, temperature, metallicity, and radial velocity that Andrew Hannington computed. And it doesn't really matter which panel you look at, but these are our simulations with this cosmic ray model, with the lower diffusion coefficient and the higher diffusion coefficient. And in all three cases, they look fairly similar. And this one on the right is more similar to the values that are used in the fire simulation I just showed you. If we switch off the interaction with the magnetic field, well, it's only this part where it loses energy, then we end up with cosmic ray dominated halos. And if you look now at, for example, the temperature panel, you can see that with a lower value of this diffusion coefficient, we end up with a very pressure dominated central CGM, so around the galaxy out to about 50 kpc. And in the case where diffusion happens faster, we actually get cool gas all the way out to the virial radius. So this, this very uncertain parameter is, I think, part of the reason why we get such different results. And then I think the different magnetic field strengths result in us having much higher cooling losses. So the higher the magnetic field strength, the more the cosmic rays lose energy to it, so the less of a cosmic ray dominated system you end up with. So here, let's focus only on the left panel. So the top purple line is this simulation where diffusion happens relatively slowly, so you get a cosmic ray dominated inner CGM if you let it build up and don't lose all your cosmic rays to the magnetic fields. The yellow one is then when we have a faster diffusion, so you get cosmic ray domination at a lower rate, but all the way out to the virial radius. And then the simulations with these alphane losses, which we do our best we can to model these, so they don't show any effect of cosmic rays because they're subdominant. And so I think we understand why there's differences, but of course we would like to know what the real truth is. And I think this is still ongoing, but there are observational repercussions. So here's the neutron hydrogen again. You've seen it before. So here we have our no cosmic ray model, and then the two that have these losses, they are effectively the same. But when we get a cosmic ray dominated inner halo or all the way out to the virial radius, we get a very different, like this halo looks very differently, and this will show up. I think it's hard to do this with these individual background sidelines, but I think 21 centimeter emission from neutral hydrogen will tell us whether or not any of this is at all anything like the real universe. So I'm hopeful that they might all not look like the real universe. I am very open to that possibility. So I have very little time left, but I will tell you in a couple minutes why you can also use these simulations not just for things that affect galaxy formation, but you can also use them to learn about chemical evolution from a sort of more galactic point of view. And I specifically want to talk about rapid neutron capture elements, which are elements that are so rare they don't really affect any of the gas dynamics in the universe, but they are cool tracers of their own origins, because we still aren't sure what makes these elements. And so this is a table that I got from the internet, from Jennifer Johnson, and you can see that in yellow is all the rapid neutron capture elements. So you see there's lots of them, but there's very low amounts of them. But if you want to know where the elements come from, this is definitely one of the important mechanisms. So let's just skip observations again. So so neutron star mergers are excellent sources of neutrons. So if you want to capture neutrons really rapidly, a neutron star merger would be a very good location for that. There are, however, these are, of course, not fully understood. And then there are kicks that happen when the first star explodes as a supernova. This supernova is never going to be perfectly symmetric. It's going to, and because we want to conserve, or we have to conserve linear momentum, the star will end up with a kick in the other direction. And how fast this kick is, we can argue about, but it could be hundreds of kilometers per second. So we now put in a very, very simple model into our cosmological simulations in order to capture this. So if you get a velocity kick of 200 kilometers per second, and it takes about 30 million years for your neutron star merger to go off, then it will have traveled 6 kiloparsecs. That is smaller than a galaxy, but there's no reason why it would travel in the galaxy disk direction. It's more likely to go in, there's more solid angle away from the galaxy. So these objects are now going to explode in the CGM. So they're not directly enriching the ISM, and you have to wait for this material to come back. But it also, so that costs extra time, which is bad if you want to match the low metallicity abundances that are observed in stars. But it helps because it decouples the other sites of metal enrichment. So neutron star mergers in this case, don't happen in the same place as supernovae. So your oxygen, magnesium, iron is all directly injected into the interstellar medium, and your R process elements are happening. So are mixing with low metallicity gas and then later accreting. Let's talk about observations. This is what you get if you just put in some fiducial parameter. So it doesn't match observations. The observations are tricky, hard to do. People might not be publishing. They're non-detection. So it's not a homogeneous sample I'm comparing to. You'll have to just forgive me for that. But if you follow the red solid curve, you can see that it really drops off at a metallicity of about -3. So these are very metal poor stars, but there's still observations of them, and they don't have as much R process enrichment as we see in stellar abundances in the galaxy. You can tweak these parameters to magically match the observations if you are so inclined. So if you make some optimistic assumptions of how many neutron star mergers there are and how they fall off, how the rate declines over time, and what the initial delay time is, you can actually do a really good job at matching the observations. And I just wanted to just make my last point that if you now don't do this with these kicks that I talked about, you now have so many neutron star mergers in the early universe that it completely collapses the distribution. So in grayscale, you can see like 1, 2, and 3 sigma. So the 1 sigma values are basically the same as the median. It's a very narrow distribution here in the bottom. Like, I mean, it maybe fluctuates by 0.1 dex up and down, and that's not at all like what the observations are showing. So previously, people have been arguing that it's because these objects are so rare, that's why you get a large scatter. And now I'm not saying that this is the final answer, but there's definitely another way to do this. They're not rare, but they get kicked out of the galaxy, and therefore you decouple the sites of metal enrichment. And that's where I'll end. Thank you. The star formation rates, so what you really would want is like a big sample rather than like, I usually do this with like a couple of galaxies, but they don't seem, so they fluctuate because chaos happens and galaxy formation isn't like always exactly, if it has a burst like half a gigayear earlier, then it can change some things, but it doesn't seem to be systematic. So the star formation history is fairly robust. So the outflows are probably doing the same sort of work in ejecting material and preventing stuff from accreting, but they're doing this in very different ways. In one case, going much wider than in the other one, which is maybe surprising. I agree. Yeah, so if you want to, so firstly, I don't know, I'm not a LIGO expert, but the stellar abundances that we're using are telling us that there should be a decent number at very high redshift, and then you have to have a sort of decline to lower redshift, or otherwise you would get an increasing trend of how much of these R process elements there are as a function of metallicity. Yeah. Yeah, so that would, so it would help with this, because if you have a steep time dependence, so more in early universe and fewer now, relatively speaking, you have an easier time matching the stellar abundances. However, we do need to have like enough of them, just if the overall rate is really like a lot smaller than I'm assuming, we're still having a hard time enriching the early universe. So a strong decline helps, but we still need to have a high enough normalization. So I don't know how the rate that we assume, which is about I think 10 to the -4 per mega year in the Milky Way. I don't know how that compares to current estimates. It compared favorably to the binary pulsars in the Milky Way, but there's only like a handful of those. So I would love more constraints from observations on this. shouldn't have skipped that slide. Or maybe I should, and then I get to ask about it. I think one of there are many ways, but most of them are only like sort of useful in the ISM, and some of them are only useful in the ISM of a very nearby galaxy, like the one we're sitting in. So the ones that work, that I think are most promising for like the very diffuse gas external galaxies and their CGM, are rotation measure. So you have a polarized background source. It's the same as these quasar sightlines. The light moves through some gas that is between the source and the observer. And then depending on the frequency, you get more or less that this polarization angle rotates. That's why it's called a rotation measure, or also called Faraday rotation. So this depends on the electron density, the magnetic field strength. So so you have to sort of, and it's only the magnetic field strength along the line of sight. And if you had a magnetic field that like went towards you and then away from you, it cancels. So it's only what's left over. So there's sort of, it's really hard to disentangle what is the actual magnetic field strength. But what you can do is do the same thing in your simulation. So now you're calculating the rotation measure based on, you know, the density and you know the direction of the magnetic field along the line of sight, so you can also calculate it. So this is what we've done. So here there's a profile of what we get for like 6 or 7 different galaxies. This is all the way out to their virial radius. So in the center, you get higher values than in the outskirts. And then you see, when we published this, it was only upper limits, and it's very easy to match upper limits. Like everybody matches the upper limits. But since then, so I put like 2 more on this, like I just PowerPoints put it on. So there's been a fast radio burst in M81, which is like 30 kiloparsec offset, which we could argue is no longer really probing the ISM, but rather probing sort of the inner CGM, or this H1 dominated disk around it, which has a very high rotation measure, which could be consistent with our simulations. And then Hasten et al. Has done this with like low-fire observations of like a variety of polarized background sources, and then binned everything and then got that detection. But it's like big bins. So, and then everything at larger radius was like consistent with noise. So there's really, they did find that it was higher along the outflow direction, so along the minor axis, than in the plane, which we haven't technically looked at, but here is a picture of our simulation. And I think you can see that we have higher rotation measure along the minor axis than in the plane.
Next question, you compared simulations with and without magnetic field. I don't describe that, and maybe how that influences the differences that you see and some of the other quantities that you're talking about.
So this is trying to show you the morphology by convolving it with a line integral. So the part where they're taken out, it might be hard to see, but taken out by these outflows from the galaxy. This is a very recent like enhancement of the magnetic field. They're fairly elongated in this direction. So they're fairly large scale. And then if you look away from this outflow direction, they're much more sort of turbulent. We actually think, I didn't talk about this, that some of the magnetic field strength also gets amplified inside the halo through a large scale dynamo. So you have structure really on all scales. But you can only see the small scales are always faster to do, so that you can only really see the elongation where there's been like a strong movement, because it's not just the gas that follows the magnetic field. If you have a strong enough push, the magnetic field will have to follow the gas, so you get then these elongated structures. This is all just like happening, so I don't really have much control to see how, if I had a different morphology, how it would change. We could try to mess with it, but then it wouldn't really be in a stable equilibrium. So then you don't know if you were still looking at the real, the real effects, or sort of the numerical effects of changing it. Yeah. Thanks for having me.